Hi, in this video we are going to look at some right angle trigonometry using the sohcahtoa method, and we're going to look at some exam style questions that involve a bit of problem solving and a bit of preparation before we are ready to do the method. So our intention is to be able to identify a right angle triangle within a 2D shape. The triangle is not always going to be obvious. We have to then prepare the triangles. By that I mean there's maybe some numbers we need to create within the triangles, and then we're going to perform sohcahtoa, and we're going to mix it up and either find an unknown angle or a side, and sometimes you have a conclusion to do on these questions as well. So prior knowledge is you should be comfortable by now finding an angle and a side using the sohcahtoa method on basic right angle triangles only, okay? So example 1, I have a picture of a wee pair of earrings there that are made from an equilateral triangle of side 12 millimetres. So I've missed millimetres out there on the question, but it's on the diagram. Calculate the height of the earrings. So what do we know about equilateral triangles? Well, we know they're symmetrical, and they've nicely drawn in this line here, creating the height, which is kind of preparing you to the right angle triangle we're going to be using. So I'm going to extract the triangle, and that's a big part of this. So I know that this side is 12, and we want this side, I'm going to leave it as h. Now, we need to be able to know something else about this, ideally an angle. Now, an equilateral triangle, we could. It's worth pointing out, actually, we could also use Pythagoras here, okay? But we aren't going to do that today. We're going to do it using sohcahtoa. Now, an equilateral triangle means that all these angles are the exact same. So 180 divided by 3 gives us 60. So this angle down here is 60. Okay, now I could put in that the base of the triangle is 6, but I don't want to give us too much information. So we're going to label it. So across from the angle we've got opposite, across from the right angle is our hypotenuse, and the one that's left over next to the angle is adjacent. So using sohcahtoa, which formula will we use? We are going to tick off hypotenuse because we know that, and we're going to tick off our opposite because that's what we want to know. So we're left with the sine formula. So sine of our angle is O over H. Now remember our angle is 60. So sine 60 equals, now the height of the triangle is what we're after, so that's our opposite, and our hypotenuse was 12. Now remember we want rid of that divide by 12 on the right hand side, so that comes up and becomes a times by 12. So our height is, to one decimal place, is 10.39, so 10.4. So our height is 10.4 millimetres to one decimal place. And it didn't specify rounding, so I've done one decimal place. Okay, so in that question we had to spot the triangle first, and that's what's different with these examples, okay? Okay, my next one, the classic ramp question, okay? At National 4 you can get asked about the gradient of a ramp. You could also get asked about this angle in here. This is what we're basically after here. So building regulations state that the ramp had to be an angle of no more than 13.8 degrees to the ground. Does this ramp satisfy safety regulations? So there's no extra work to do on this one, okay? The triangle is obvious. It's just deciding that that's the angle we're after there. So we're going to label it. Across from the angle is my opposite. Across from the right angle is my hypotenuse. And the base there with nothing on it is the adjacent. So writing out sohcahtoa, we are going to tick off the ones we know. We know opposite and height. So it's just coincidence that it's sine again for this one. So sine of my angle equals O over H. So sine of my angle is 0.6 over 2.7. Now remember the angle ones is the one that used the shift or the inverse or second function button in your calculator. So it's inverse sine of 0.6 divided by 2.7. And that gives us, to one decimal place, it goes to 12.8 degrees. Now let's read the question again. It said regulations state the ramp had to be an angle of no more than 13.8. So 13.8 is the maximum it can be. So is this okay? So since 12.8 is less than that, so since 12.8 degrees is less than 13.8 degrees, the ramp passes regulations. Okay, there must be a numerical comparison in there. You can't just say, yes, it's okay. Okay, you have to say that 12.8 is less than 13.8. If you're not sure of the less than symbol, write it in words. Okay, you could even say, oh, it's 1 degree less than it needs to be, so it's okay, something like that. All right. My third and final example, we have a rhombus here, so it's casting our minds back to knowledge of rhombus. Now, a rhombus has all 4 sides the same, so I'm going to put these lines in to remind us that these are all equal. They want that shaded blue angle there. Now, this is not a right angle triangle, so I can't actually find out that angle right now. What I can do is extract one of the right angle triangles, and I can get this angle here. Okay, now that angle is just half of that one, so what I'm going to do is I'm going to find angle X and just double it, because these diagonals here in the rhombus act as lines of symmetry. So this is one where I have to prepare the triangle. I'm not going to use 8 and 18 because 18 is a full diagonal, so half of that would give me 9 going from left to right, and then half of the 8 up and down would give me 4. Let's label the triangle. You should also obviously remember that the diagonals of a rhombus meet at right angles. If you don't realise that, then we can't really proceed. Across from the angle then is opposite. Across from the right angle is height, and the one that's left next to the angle is adjacent. So, sohcahtoa. What ones are we going to tick this time? So we are going to tick off adjacent and opposite. So adjacent and opposite. So it's tan. So tan of our angle is OA, O over A. We don't know the angle, so it stays as X. Our opposite is 9 and our adjacent is 4. This is the one where we're going to do shift tan or inverse tan. 9 divided by 4. Please remember you can write that as a fraction, 9 over 4 inside the brackets again. Don't forget the brackets, your calculator may already bring them up for you, depending on the brand. And this gives us an answer of 66.0 degrees. So let's just say it's 66 degrees. Now that's what X is. Do we need to conclude the question? So the shaded angle is double that. So shaded angle is 66 doubled, which is 132 degrees. And that can match the picture because it is an obtuse angle. Okay. So what I'd like to do is go try these ones for yourself. In each one it's important that you identify the right angle triangle. So these two here are just a case of splitting it straight down the middle and using symmetry. You've got equilateral triangles, you've got isosceles triangles, so I didn't do one like that, but it's very much the same. You're going to split it down the middle in half the 14. And then I've got 2 rhombus ones where you have to kind of do what I did in example 3. So have a pause, try these, and then check your answers. So what have we learned? Hopefully you've learned how to spot right angle triangles within 2D shapes. It is usually isosceles, equilateral triangles, and the odd rhombus thrown in, maybe a kite. And hopefully we've learned how to calculate the required side at angle and answer your question in context. And we spoke about if it is a does this meet requirements one, you must do a numerical comparison. Okay, thank you and good luck.